In this lesson, we want to learn about solving polynomial inequalities. All right, so previously we talked about how to solve quadratic inequalities. If you remember how to do that, the process for solving polynomial inequalities is exactly the same. It's just that in this section, you're going to be dealing with some polynomial functions that are of degree 3 or higher, whereas in the section where you dealt with quadratic inequalities, all of the polynomial functions you dealt with were of degree 2. So this is just going to be a lot more tedious. So I have here for the procedure, we're going to rewrite the inequality so the right side is 0. So the problems I'm going to give to you, and also in a lot of books, they're factored. So this really isn't as much of an issue as when we dealt with quadratic inequalities. But if it's not given to you in factored form, just move all your terms to one side of the inequality. So let's just say the left side, we're going to call that f of x. That's going to be our polynomial function we're dealing with. And then the right side should be 0. So this less than here will have f of x is less than 0. I have the less than can be replaced with the appropriate inequality symbol. So it might be greater than, less than or equal to, or greater than or equal to, just depending on what you get in your problem. Then I have to replace the inequality symbol with an equality symbol. And then we're going to solve the resulting equation. So we're solving the equation, f of x, again, that's the polynomial function that we set up, is equal to 0. So the solutions to the above equation are known as the zeros. So we've talked a lot about that in this section. We know that the real zeros to the above equation correspond to x-intercepts on the graph. This right here is extremely important to understand for this section. Then we have here that the non-real complex zeros, because you can get those as well, will not, okay, let me read that again, will not correspond to x-intercepts on the graph. Let me come down here and read the rest. I have used the real zeros to create intervals on the number line. So in other words, you can make a number line, and I've already pre-drawn everything here, but just draw a horizontal number line. You can label it as the x-axis, and you're going to think about, well, those real zeros are going to give me my x-intercepts. You can mark those off and say, well, now I can use that to create intervals on the number line. And once you have those intervals, you can use a sign chart, or again, a test point, to find the sign in each interval. When you have some of these polynomial inequalities, it's very time consuming when you're plugging things in. So I would actually recommend in this situation to use a sign chart and not to get a point. So now I have put the solution together based on the inequality given. So the solution will contain any region that makes the inequality true. The endpoints are included for a non-strict inequality, and then the endpoints are excluded for a strict inequality. So this is very important to understand. Again, when I say endpoints, I mean the critical values, or again, you can think about these as the real zeros that we use to create those intervals on the number line. All right, so we're just going to take a few moments and think about where that procedure comes from and why does it work. So I have here, since the graph of a polynomial function is continuous. So we know what that means. It means we can sketch the graph without picking up the pencil from the paper. So I have here no holes or breaks in the graph. So its sign is only going to change from positive to negative or negative to positive by first crossing through the x-axis where the function value is 0. So we should know on the x-axis that the y value or the function value is 0. So this means between consecutive real zeros, which correspond to x-intercepts on the graph, the sign of the polynomial function is either always positive when we are above the x-axis or always negative when we are below the x-axis. So this right here is what leads to our procedure. All right, so coming down to the graph, I'll give you a quick visual explanation of what I just read. So you have something like f of x equals the quantity x minus 2 times the quantity x plus 1 times the quantity x minus 0.5 times the quantity x minus 3. So if I said find the zeros for this polynomial function, we know that we could take this right here, set it equal to 0 and solve, or we could just write everything in the form of x minus k, where k is the 0. So in other words, this 0 would be 2. This one, you'd have to change it over into minus a negative 1. So let me just arrow to that and just say this would be changed to x minus a negative 1. Just so this is clear. So the 0 will be negative 1. This one is x minus 0.5, so it's just 0.5. This one's x minus 3, so it's just 3. So you'd have a 0 of 2. So that corresponds to this x-intercept right here, which is 2, 0. You have a 0 of negative 1. That corresponds to this x-intercept, which is negative 1, 0. You have a 0 of 0.5, which corresponds to this x-intercept, which is 0.5, 0. And then you have a 0 of 3, which corresponds to this x-intercept, which is 3, 0. So what we said above was that basically the sign of this function, so when we think about the y value or the function value, so it can only change from positive to negative or negative to positive by first crossing through the x-axis. So in other words, going through an x-intercept. So if you can find the x-intercepts, then you know that you can create intervals, and those intervals can be used to test. So one interval would be anything less than negative 1. Another interval would be between negative 1 and 0.5. Another one would be between 0.5 and 2. Another one would be between 2 and 3. And then the last one would be anything greater than 3. Because I know in the interval where x is less than -1, you can see that it's always positive. Then between -1 and 0.5, it's always negative. Then between 0.5 and 2, it's always positive. Between 2 and 3, it's always negative. And then anything greater than 3, it's always positive. So all you have to do, once you've found your x-intercepts, you use those x values to set up your intervals. You just pick something for x in that interval, plug it in, and then if your function value is positive, then it's always positive in that interval. If it's negative, then it's always negative in that interval. So very quickly, if I asked you, just looking at the graph, not doing any kind of algebra or anything, let's say we had x minus 2, and then times x plus 1, and then times x minus 0.5, and then times x minus 3. If I asked you, where is this less than 0? Again, just look at the graph, and you would say, what are the x values for which the y values are less than 0? In other words, what x values can I plug in over here on the left such that this right here, this left side, would be less than 0, and this inequality would be satisfied? Where you're looking at this part right here, where the function values or the y values are less than 0 because we're below the x-axis, and then this part right here. So in other words, if I wanted to solve this guy right here, I would just say that x is greater than -1 and less than 0.5, or again, you could put 1/2, or also right here. So x is greater than 2 and less than 3. All right, let's take a look at the first problem. So we're going to see that we have x minus 2, that quantity, times the quantity x plus 1, times the quantity x minus 0.5, times the quantity x minus 3. This is greater than 0. So this guy right here, again, this is your polynomial function that you're working with. And I'm giving you everything in factored form because it just makes it a little bit quicker. So this guy right here, the first thing is you would just replace this with equals. And you would solve this, so x minus 2, that quantity times the quantity. I'm going to change this to x minus a -1, like we did before. And this would be x minus 0.5, and this would be x minus 3. So if it's in the form of x minus k, again, you don't have to use the zero product property. You could do that. You could say x minus 2 equals 0, solve that, then or x minus a -1, or you could do x plus 1 equals 0, solve that, so on and so forth, and just keep going. But if it's in the form of x minus k, just take the k as the 0. So the zeros here, the zeros, you would have 2, -1, you would have 0.5, and then 3. So the only mistake that I see people making is not rewriting stuff that's something like x plus 1. Remember, it's got to be x minus k. So if it's x plus 1, change it over to x minus a -1. So these right here, again, let me paste this in. If you think about the zeros, again, if they're real zeros, they correspond to x-intercepts on the graph. So I just have my x-axis here, just so we can see this. So your 0 of 2, again, you get an x-intercept of 2, 0. Your 0 of -1, you get an x-intercept of -1, 0. Your 0 of 0.5, you get an x-intercept of 0.5, 0. Then your 0 of 3, you get an x-intercept of 3, 0. So again, we're going to have an interval where x is less than -1. We're going to test there. We're going to have an interval between -1 and 0.5. We're going to test there. We're going to have an interval between 0.5 and 2. We're going to test there. We're going to have an interval between 2 and 3. We're going to test there. And then we're going to have an interval where we're greater than 3. So you have your intervals, anything less than -1, between -1 and 0.5, between 0.5 and 2, between 2 and 3, and then anything greater than 3. So if you look at this factor right here, x plus 1, we know that it would be positive. Again, you could just solve the inequality. Let me do this to the side. Something like x plus 1 is greater than 0. Subtract 1 away from each side. So this is true wherever x is greater than -1. So that's going to be for anything here, 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 or here. But in this one right here, where we're less than -1, it would be negative. Using a similar thought process, you could fill out the rest of this table. Okay, so this guy right here, this x minus 0.5, that factor, it would be negative here and here, and then positive here, here, and here. And then this x minus 2, that would be negative here, here, and here, and then positive here and here. And then x minus 3, that would be negative here, 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 and here, and then positive here. So setting this up is pretty quick. Again, if you want to do the plugging in method, that's fine. Sometimes it's faster, it just depends. But you're just going to look through and see, do I have an odd number of negative factors, or do I have an even number of negative factors? Here you have 1, 2, 3, 4 odd negative factors. So 4 is an even number. So the result of this guy would be positive when these guys get multiplied together. Then this guy right here, you have 1, 2, 3 negative factors. That's an odd number. So this would be negative. Then here you have 2 negative factors. So that's a positive. And then here you have 1 negative factor. So that's a negative. And then here you have no negative factors, right? So it's all positive. So it's positive. So if we think about the intervals where this guy is going to be positive, it's anything that's less than -1, it's anything that's between 0.5 and 2, and then anything greater than 3. Let me come up here, a little bit easier to see. So I'm going to say that my solution is going to be x is anything where we're less than -1. Then I'll put or. We're going to have between 0.5 and 2. So x is greater than 0.5, or again, you can use 1/2, and less than 2. And then I'll put or again. We're going to have anything where x is greater than 3. So x is greater than 3. Let me go ahead and grab this, and I'll just paste this in. So this is one way to write it. A lot of times people like to write this in interval notation. So for interval notation, you're going to have coming from negative infinity, going up to and excluding -1, and then you want to use a union symbol. So this one right here is going to be, again, everything's excluded here because we had a strict inequality. So between 0.5 and 2. So again, nothing's included, so you're using a parenthesis at each end, and then the union with, you're going to have anything that's greater than 3. So just like that. And then if you want to do this on the number line, let's see, we want anything that's less than -1. So again, I'm going to use a parenthesis there. If you want, you can also do the open circle like that. But this is what I've always used, so I'm just going to stick with that. And just shade everything to the left. And then you also have between 0.5 and 2. Let's shade that. And then you have anything that's greater than 3. So let's shade that. So that would be your answer. And let me paste this in. So we've already seen this. So if I'm looking again at the graph for confirmation, and I left you a Desmos link for everything so you can just look at it. We're saying that this guy right here is greater than 0, where x is less than -1. Yeah, that's true. Look at the function values here, or the y values. They're positive when x is less than -1. Then if you look between x values of 0.5 and 2, again, that's going to be this part right here. Again, we're above the x-axis, so the function values or the y values are positive. Then again, when x is greater than 3, so that's going to be right here. Again, your function values are going to be positive. All right, let's take a look at another example. So here we have 1/12 times the quantity 2x minus 5 times the quantity x minus 5 times the quantity x plus 4 is less than or equal to 0. The first thing I would do here is get rid of this 1/12. It's not going to change your answer. So 2x minus 5, that quantity, and then times the quantity x minus 5 times the quantity x plus 4, multiplying both sides by 12, that's not going to change the solution at all. So this right here, you can just say it's less than or equal to 0, and we're just going to work with this form right here. It's just a lot easier to do. Let me just put a little border here, like that. When we graph it, we'll graph the original one, but if you want to graph this on Desmos, you'll see the answer is exactly the same. So again, you can set this equal to 0, and so now I have this quantity 2x minus 5 times the quantity x minus 5 times the quantity x plus 4. And you could use the zero product property here. So again, you could set each one of these equal to 0 and you could solve. But again, I think it's easier just to put everything in the form of x minus k. This one's a problem because you have 2x minus 5. So you could just pull the 2 out. So 2x divided by 2 would be x. And then -5 divided by 2 would be -5 halves. So this is x minus 5 halves. So let me actually rewrite this one. So I'm going to change x plus 4 into x minus a -4, just so this is crystal clear. Don't want to lose anybody. And actually, let me change that over to that. So this is equal to 0. Okay, so I can just grab the zeros now. So it's going to be 5 halves, 5, and then -4. So let me write that out. So the zeros, that's going to be 5 halves. You're going to have 5, and then -4. So let me grab this and come down here. So all we really need to know are what are those x-intercepts going to be, or what are the x values for that, so that we can, again, set up those intervals on the number line and then test inside of each interval. So you have one x-intercept that's going to be -4, 0, again, because we have a 0 of -4. You have another one that's going to be 2.5, 0, because we have this 0 of 5 halves, which is 2.5. Then we have another one that's 5, 0, because we have a 0 of 5. So we're going to have an interval where x is less than -4. We're going to have one between -4 and 2.5, one between 2.5 and 5, and then one that's greater than 5. Now, I went ahead and set up the table. So we have these factors right here. Again, if you just want to plug something into this in each interval and see if it works, is it positive, is it negative? That's up to you. Sometimes that's faster, sometimes it's not. Again, it's just based on the problem. Again, you had that 1/12 out in front when we started. Remember, that's not really going to change anything because it's just a positive number that's multiplying all these factors right here. So again, you could just get rid of it. We multiply both sides by 12. The answer will be the same. When we graph it, it'll look different, but the answer will be the same. So this guy right here, this x plus 4, would be negative here, positive, 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 because it would be positive for any x value where we're greater than -4. Then 2x minus 5, that would be negative here and here, and then positive here and here, because that would be positive for any x value that's greater than 2.5. Then x minus 5, that would be negative here, here, and here, and then positive here. That would be positive for any x value that's greater than 5. And then this guy right here, again, all you're doing is you're looking at, do I have an odd number of negative factors? Well, here it's 1, 2, 3. That's odd, so I'm going to get a negative. This is positive, negative, negative. That's an even number of negatives, so this is positive. This is positive, positive, negative. 1 is an odd number, so an odd number of negatives, you're going to get a negative. And then this is all positive here, so this would be positive. So what you can say is that for the less than or equal to scenario here, we would say that x is less than or equal to -4, then or you're going to have that x is greater than or equal to your 2.5 and less than or equal to 5. So this is what you want. Let me grab this. And again, if you want to do interval notation, so these are all going to be included because, again, we had a non-strict inequality. So here we would say coming from a negative infinity, going up to and including -4, and then the union with, you can have anything between 2.5 and 5, with both of those guys being included. Okay, so looking at the graph, let me fix this right here. You want to say, you can put a bracket at -4, or again, if you want to do a filled in circle like that, that works as well. I'm just normally using a bracket, so I want to stay consistent. So at -4, maybe that's a little bit too far to the left, so let's do it like that. So the other one would be between 2.5 and 5. We'll just shade all of that. Now let me grab this. All right, so coming down here, again, I'm using the original f of x equals 1/12 times the quantity 2x minus 5 times the quantity x minus 5 times the quantity x plus 4. I gave you a Desmos link. If you want to put your cursor right here and delete this right here, you'll see that the graph is going to change. It's a different function you're working with, but the solution would still be the same. So if you look at this, we're looking for where, again, this part right here is either 0 or less than 0. So you would have a solution at -4, 0, and then anything to the left in terms of the x value. So anything that's -4 or less, so x is less than or equal to -4. So that's this part right here. Then also, this would be true where x is greater than or equal to 2.5, there's 2.5 right there, and less than or equal to 5, there's 5 right there. So all of these values right here. All right, let's take a look at one final problem. So this one has a few things in it that I think are important to understand. So we have the quantity 2x squared plus 5x plus 4 times the quantity x minus 1 squared times the quantity x minus 2 is greater than 0. So first, let's just write this as 2x squared plus 5x plus 4. And then this right here, x minus 1 quantity squared. And this one right here is x minus 2. And let's set this equal to 0. So we know that we would have zeros in terms of real zeros. Let me put that here so I am more specific here. Let me put real zeros of 1. Now notice the multiplicity is 2. So that means when we get to our x-intercept at 1, 0, it's going to touch and turn around. Let me show you that real quick. I'm hoping you remember that from our lesson. Here's that x-intercept of 1, 0. Again, we're negative, negative, negative. We're going to touch and then turn around. Okay, because there is no sign change on this side to this side because of the squaring operation. The 2, 0, well, that one, the multiplicity is 1, so it just goes straight through. This side of it is negative, this side of it's positive. So again, we talked about that earlier. Let me go back. So the real zeros, we have 1, and then we're going to have 2. Now, what about this guy right here? Well, you should know that you can use something called the discriminant, and that is b squared minus 4ac, and you want to see is that negative. If it is, again, that's the part under the square root on your quadratic formula that tells you you're going to have two non-real complex solutions. So this right here is your a, this is your b, and this is your c. So b squared minus 4ac, you want to see if that's negative. So b is 5. 5 squared is 25. And then a would be 2. And c would be 4. So 4 times 2 is 8. 8 times 4 is 32. So what is 25 minus 32? That is going to be negative 7. Because this guy does not have any real zeros involved, and I'm talking about this specifically right here, when you look at it, it's not going to have any x-intercepts. So this guy is either always positive or always negative. Let me come down. I'm just going to show you this with a graph. So this is f of x equals 2x squared plus 5x plus 4. Again, there are no real zeros for this, so you see that it does not touch the x-axis ever. So it's either always positive, so it's above the x-axis, or it's always negative, meaning it's below the x-axis. Here from the graph, you can see that it's always going to be positive. No matter what x value I pick and plug in, it's always positive. And all you have to do in this scenario is pick something, usually you just pick 0, plug it in, and see what you get. So here, if you plug in a 0, so f of 0, you would get, this is going to go away, this is going to go away, you just have 4. You can see you have this point right here, which is 0, 4. But that 4 right there is positive, so it tells me that this guy's always going to be positive. So just keep that in mind. When we come down to set up our intervals, again, the only things I'm going to worry about were the real zeros. So I had a real zero of 1, so I get 1, 0, and I had a real zero of 2, so I get 2, 0. But again, remember the behavior of this guy, the multiplicity of this was 2, so it's going to touch and turn around there, whereas this one, the multiplicity was 1, so it's going to cross through. So that's something you just want to keep in mind. You're still going to split this up into intervals, so anything less than 1, anything between 1 and 2, and then anything greater than 2. This 2x squared plus 5x plus 4, again, we know it's always going to be positive. It will never be 0, and it will never be negative. We saw that earlier. So I put positive, positive, positive. this x minus 1 quantity squared. Again, that's either going to be 0 when x is 1. Again, that's at your x-intercept, so 1 comma 0. And it's going to be positive everywhere else because of the squaring operation. So positive, positive, positive. So really, this other factor of x minus 2 is going to determine everything. So if you have something like x minus 2 is greater than 0, add 2 to both sides of the inequality. That cancels, you get x is greater than 2. So x needs to be greater than 2 for this to be positive. So in this interval, it's negative. In this interval, it's negative. And then here, where we're greater than 2, it's positive. So if you look, you have positive, positive, negative, so that's going to give me a negative. Positive, positive, negative, that's going to give me a negative, and then positive, 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 that's going to give me a positive. We're really only going to say that the answer here is where x is greater than 2 and strictly greater than 2. Let me come down here and say that x is greater than 2. In interval notation, this is just 2 going out to positive infinity. Again, make sure that you use a parenthesis next to 2, it's not included. And so here, again, you could put an open circle, or I'm going to use a parenthesis there, and then just shade everything to the right like that. And again, just looking at this on the graph, because this 0 had a multiplicity of 2, it was even, it touches and turns around. So it's negative, negative, negative. It's going to go to 0 at an x value of 1. Then it's going to go back to negative, 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 negative. And it's not going to get to positive until we get past an x value of 2. So at an x value of 2, again, this guy is going to be 0. But anything to the right of 2 in terms of the x value, now we're finally going to have a function value that's positive because this is positive. So for anything there that x is greater than 2, we would have a function value that is positive, or you could say a y value that's positive. So not 2 itself, but anything greater than 2. So that's this piece of the graph right there.